about photometry, mineralogy, and optical maturity of lunar surface features. Right, thanks.
All right, thanks, Tim. All right, so I realize that my title is a little bit vague, so I have a second title. This is what I'm actually going to be talking to you about, is new insights into the origin of the South Pole Aitken Basin thorium hotspots. So this is some work that's kind of being done through PSI's survey team, TREX, not T-Rex, TREX. So the motivation behind this work is basically to look at the composition and physical nature of the small northwestern SPA thorium hotspots, which you can kind of see here. I'll show them better in a couple more slides, and to determine the origin of the elevated thorium. So we're doing this by integrating higher resolution data sets than have been used before to look at these thorium hotspots. And then the results of this work will ultimately aid in understanding the abundance and variability of creep-rich materials on the moon, as well as looking at implications for the geochemical and volcanic history of the moon. So this is an image we've seen a few times already this week. This is the Lunar Prospector Gamma Ray Spectrometer Thorium map. You can see that here's the near side. We've got the procelarium creep terrain that stands out really well in thorium, as well as SPA on the far side. And again, the two thorium hotspots I'm going to be looking at are over here. Sorry, this pointer's a little hard to use. So let me backtrack a little bit and give you a little bit of background on the thorium hotspots in SPA. So overall, the SPA basin has an elevated thorium abundance, most likely due to exposure of noritic type materials. And then there are these two localized thorium hotspots, again, here and here. So there's been a couple of theories over the years as to the origin of these hotspots. For a while, the leading theory was that these are related to Imbrium or Serenitatis ejecta, as they actually lie antipodal to those two basins. But more recent theories have suggested that these are actually indigenous to the basin itself, and that were later exposed by smaller cratering events. And as a result of these kind of earlier theories, there's been these models for kind of the evolution of the moon that suggest that the entire moon underwent fractional crystallization, which resulted in the anorthositic crust, as well as a stratified lunar mantle with a creep layer sandwiched between the crust and mantle. And then these models suggest that the SPA forming impact mobilized this creep component, concentrated it on the near side, which then later formed the procelarium creep terrain that you saw on the previous slide. And at the same time, the impact kind of induced the sinking of ilmenite pods, which later served as TI-rich source regions for the basaltic volcanism we see within the far side in SPA. And the SPA exposed Mare basalts actually do not have enriched thorium signatures like they do on the near side. So obviously understanding the origin of these hotspots then will kind of really have important implications for understanding these evolution models. So let's zoom in a little bit to look at the thorium hotspots that I'm talking about in SPA. We have two. There's one here that's kind of centered on the westernmost part of the kind of rim and ejecta of Birkeland crater, and then the southernmost one here is more or less centered on the Oresme V crater, which superposes Oresme U. And I want to zoom in on this hotspot because most of what I'm going to show you for the rest of the talk kind of centers on the Oresme VU thorium hotspot. And then this inset here, let's see if I can get this working. This is kind of an area I'm going to focus a lot on with NAC imagery, so looking at this area more kind of on the meter scale. So like I said, we're going to be using a lot of higher resolution data sets than have been used before, and kind of just integrating multiple data sets to try to get at the nature and origin of these hotspots. So first, I'm going to be looking at LROC NAC imagery. So this is kind of more on the meter scale, coupling that with NAC digital terrain models and HAPKI photometric modeling to kind of get at physical and compositional properties, again, at the meter scale. And then looking at optical maturity using OMAT, and then finally mineralogy using M-cubed spectral data, and eventually we'd like to also use wax spectral data, but not quite to that point yet. So first I'll talk about the NAC photometry. So we're using NAC images coupled with digital terrain models to produce photometric parameter maps. So these reveal changes in specific photometric parameters, again, at the meter scale. We look at parameters that depend on things like composition and physical properties. So we create these maps using nonlinear optimization techniques to minimize a modified form of the Hapke function that then gives us optimal values for parameters we're interested in. And you're in luck because I'm showing the equation and I'm not going to talk about it. The parameters of interest in this equation that we're looking at for this work are the single scattering albedo, which depends largely on composition, and then B, which is related to scattering properties and depends a lot on specific scattering properties of particles as well as their grain size and shape. And then this image here is just kind of showing the NAC DTM overlaying on an image, a NAC image. And we cannot do this without NAC DTMs because the DTMs actually feed into the model and give us values for local incidence emission angles at each pixel in the image. So again, we can only do these NAC scale photometric maps where we have NAC digital terrain models. And we happen to have one that covers the Oresme V crater, part of Oresme V and Oresme U, and then the rim in between. So here are the photometric parameter maps that we generated. The image on the left here is just the reflectance from the original NAC image. And then this single scattering albedo map here in the middle. I'm about to give up on this laser pointer. And then the B map here on the right. And I'm showing this just to kind of show you that there's really nothing going on in the scene other than the fresh crater that's at the north. I know the colors aren't the best on the screen here, so if you want to see these later, let me know. But yeah, so there's really just not much going on. The single scattering albedo values and the B values are fairly constant throughout the whole scene. Now, I have done some previous work correlating mafic mineralogy with single scattering albedo using Apollo and Luna sample data, and that's shown here. And so I was just curious, where does the Oresme VU value fall in relation to this? And it's kind of this purple spot over here. That has a very similar value to that of the Apollo 14 creepy impact melt breccias. I don't know yet if this has any significance. This is only one data point. But overall, there's nothing remarkable going on here. So then decided to move on and look at optical maturity of the Oresme VU thorium hotspot. Again, using OMAT data, so basically all you're looking at here are brighter regions are less mature, fresher surfaces, darker regions are more mature. You can actually see that the Oresme U crater is a little bit darker than Oresme V, but it's obviously older, so that's not surprising. So again, there's nothing remarkable going on here. So the next, we decided to look at compositional diversity within SPA. So working a lot with Dan Moriarty on this. Dan and Carly actually identified 4 distinct mineralogical zones in SPA, and he's going to talk a lot more about this at 2:30, so I'm just going to touch on a couple things and kind of leave it up to him to discuss the rest. But 2 of these zones actually have elevated pyroxene abundance. We have SPACA kind of here in the middle, and then which is dominated by calcium and iron-rich pyroxenes, likely experienced extensive non-basaltic resurfacing. And then right outside SPACA is the MG pyroxene annulus, where the composition is more dominated by MG-rich pyroxenes, and likely represents more excavated deep crust and upper mantle materials. And just to orient yourself, the 2 stars are Oresme V and Birkeland. Oresme V falls in the MG pyroxene annulus, and then Birkeland crater falls in the heterogeneous annulus, which has more feldspathic materials but does have localized regions of pyroxene. Moving on, so again, Dan looked at some M-cube spectral data. This is showing band depth. So in SPA, we can really capture kind of the spectral diversity of materials in the near infrared used by looking at the composition and abundance of pyroxenes. So here, band depth is sensitive to pyroxene abundance. So in this image, kind of the blues and greens are lower pyroxene abundance. The reds and yellows are higher pyroxene. You can see kind of some of the exposed Mare basalts have more kind of red going on, so they obviously have more pyroxene. And in the Oresme VU area, we just have an overall low pyroxene abundance. So again, unremarkable. But don't fall asleep yet, because we do actually have something interesting to talk about. So moving on, looking at the 1 micron band center, which is sensitive to pyroxene composition. So here, your blues and purples are your MG-rich pyroxenes, which again are common in this area in the MG pyroxene annulus. And the reds are more calcium and iron-rich pyroxenes. So we're actually looking at Oresme V. We start to see some more of these long wavelength absorption bands kind of on the western rim. If I can get this to, I can't get this to work. So over here. And if we actually look at the 2-micron absorption band, we start to see this even more kind of distinctly. So you can look at, you see the Mare basalts again, they have the calcium iron-rich pyroxenes, which we expect to see. But then here on the rim and ejecta of Oresme V, we're starting to see this signature. And the area that we had the NAC coverage was actually right down here in the blue area, which is the typical Mg-rich pyroxenes that you see in the area. So that may explain why we didn't really see anything remarkable going on there. So we decided to look and see if we see this signature as well on the the eastern portion of Oresme, as well as at the Birkeland crater where the other thorium hotspot is. And we actually do see these similar calcium iron-rich pyroxene signatures on the rims of both of these craters. And the signature is actually even more pronounced at Birkeland. So what does all of this mean? Just to kind of summarize real quick. So again, the Oresme VU thorium hotspot is really unremarkable in OMAT data, as well as in the current available NAC imagery and photometric parameter maps. Again, we don't have extensive coverage here, and we only have one area we can do the parameter maps. So that's something to go back and look at. But the materials on the rims and ejecta of Oresme V and Birkeland kind of exhibit these more basalt-like pyroxene compositions, which is really unusual for this area of SPA. As Dan mentioned, the compositional relationship between kind of the walls and the peak of Oresme V and Birkeland is similar to what we see more in the Spaka terrain. So our working hypothesis, again, this work is kind of still new and in progress, but what we're thinking is that the Oresme V and Birkeland forming impacts actually tapped shallow, a near-surface thorium-rich igneous intrusion that then resulted in the observed thorium hotspots. And this intrusion would have to be shallow because the peaks of the craters actually still have the Mg-rich signatures that indicates they're bringing up things from depth that are not this calcium iron-rich material. So kind of some future work. Like I said, this is kind of a newer project, work in progress, is to look at some more M-cubed analysis, look at the western edge of Birkeland and see what we see there, do some more comparisons with Spaka materials, and then go back and do some more photometric analysis of the western Oresme V rim. We're targeting some more NAC images now, because we can do some photometric modeling even if we don't have DTMs, but we need to have the right kind of NAC coverage. And then to also go back and look at Birkeland with photometric analysis. So we do have stereo coverage right in the middle of that thorium hotspot. We've requested a DTM to be made so we can produce these photometric parameter maps and then compare them with the Oresme V hotspot. So stay tuned, but that's what we're looking at so far. So thank you.
Okay, thank you. Something I should have mentioned actually is that Ariel Deutsch's talk next has been cancelled. So, so we've got a little bit of time for questions here. And this actually should help get us back on schedule for Patrick's talk at 10:05. So do you have any questions? Oh, Bill.
Yeah, I was just curious because you know, the implantation model from Imbrium and the rest is interesting, right? So, so you found anomalies with these two craters. Just as a check, are these so anomalous that we don't see them anywhere else in SPA? Have you done sort of a broad search to see whether these regions are really unique in terms of this feature?
I have not done the broad search. I mean, there's been a lot of previous work that's looked at the thorium signature in SPA, and it is only these two. I mean, overall, SPA has a higher thorium signature than the Highlands materials.
Oh, I guess what I meant is that
you don't mean.
I mean, you're looking at these two craters. You're looking for a specific feature to see, are they different than everything else? I guess my question, do you see that feature that you just found in other craters in SPA? That would be sort of a way to, alternative way to test this.
I may actually let Dan answer that because he's done the M-cubed analysis, but.
Yeah, so seeing those kind of salt-like compositions. Sorry to be standing a foot away, but talking through a microphone at you. But right, so we don't see basaltic compositions like that in impact crater walls outside of like huge Mare patches. So it's a really unusual thing to see two craters specifically associated with these thorium hotspots having basaltic compositions in their wall. So it's really, it kind of stands out. It is remarkable.
Okay, so it really is an exception. Okay, that's all.
I'll be talking more about that in my talk this afternoon.
Okay.
Okay.
I think I'm gonna
David?
Yes, Ryan. So I guess I have two questions. If we think of them as plutons, I guess the first question I have is there a gravity signature of that pluton? And the second question I have is, those would be huge plutons. Okay, so I don't know what the dimensions are there. I forget what they are, but
not 100% sure. I think the one crater is about 50 kilometers, or as may be.
okay, so the plutons could be tens to actually in excess of 100 kilometers in diameter. So I'm wondering, is an intrusion of that size reasonable?
Yeah, I don't know the answer to your question, especially about gravity. I have not looked at gravity yet, but that would be a good thing to go back and look at. And I guess I am curious too, if I go back, we haven't looked at the M-cube data in between these two thorium hotspots, so I am curious if we're going to see anything in between the two, or kind of what. So yeah, I don't know if that's a reasonable size. It's just kind of our first theory that's kind of popped to mind looking at this. So yeah, I think there's a lot more work to go back and look at to see if this is reasonable in terms of, you know, size and then composition and everything. So.
Okay, we've still got a few more minutes. Are there any other questions or discussion points anybody wants to make? Okay, I guess not. All right.